Section: Introduction. In this introduction, we're discussing a key technique in computer vision known as masked image modeling. One recent development in this area is the use of masked autoencoders, MAE. These models are given a small, random selection of visible image patches and are then tasked with filling in the missing pixels. By focusing on this small selection of visible tokens, MAE can efficiently train large models on extensive vision datasets, yielding impressive results across a range of tasks. The MAE framework uses a method called multi-headed self-attention to perform this self-supervised reconstruction task. This means that the masked and visible tokens not only interact with each other but also with themselves, creating a comprehensive and contextually aware representation. However, the masked tokens themselves don't contain any information. We might think that allowing these nearby masked tokens to exchange information would help the model create a more consistent image, but we question whether dense self-attention is really necessary for learning a good representation. We examine two parallel components involved in decoding each masked token: self-attention with other masked tokens, and cross-attention to the encoded visible tokens. If MAE relies on self-attention with other masked tokens, its average should be on par with the cross-attention. However, our comparison shows that the magnitude of cross-attention from masked tokens to visible tokens in the MAE decoder is much greater than that of self-attention between masked tokens. This leads us to ask two questions. 1. Is the self-attention mechanism within masked tokens in the decoder truly necessary for effective representation learning? 2. If not, can each patch be independently generated, allowing the reconstruction of only a small subset of masked patches, which in turn can facilitate faster pre-training without sacrificing downstream performance? To address these questions, we introduce CrossMAE, which differs from MAE in three ways. 1. Cross-attention for decoding. Instead of passing a combination of masked and visible tokens to a self-attention decoder, CrossMAE uses masked tokens to query the visible tokens in a cross-attention decoder to reconstruct the masked patches. This reduces the sequence length for the decoder and cuts down computational costs. 2. Partial reconstruction. After removing self-attention, the decoding of each masked token becomes conditionally independent from one another. This allows for the decoding of only a fraction of masked tokens rather than the entire image. 3. Interblock attention. We propose a lightweight interblock attention mechanism that allows the CrossMAE decoder to dynamically leverage a mix of low-level and high-level feature maps from the encoder, improving the learned representation. Our training results show that a VID encoder pre-trained with the reconstruction objective can learn a comprehensive representation of the image regardless of whether self-attention is used in the decoder. Surprisingly, the downstream performance of CrossMAE is on par with MAE, while maintaining a higher efficiency enabled by cross-attention and partial reconstruction. We show that a VIT-B model trained with CrossMAE partial reconstruction achieves a classification accuracy of 83.5% on the ImageNet validation set, which surpasses its full reconstruction MAE counterpart. In object detection and instance segmentation on COCO, CrossMAE achieves 52.1 AP and 46.3 AP, again surpassing MAE. Finally, we show that with VIT-L, CrossMAE enjoys improved scalability when compared to MAE. In the realm of self-supervised learning, SSL, a model trains on a pretext task where the supervision comes from the input data itself without relying on labeled data. Contrastive learning is a popular approach to SSL that aims to learn representations by contrasting positive and negative samples. An alternative method for self-supervised learning is generative modeling, which focuses on acquiring a generative model capable of capturing the underlying data distribution. After the pre-training stage, these generative models can be fine-tuned for many downstream applications. Section summary. Masked image modeling, specifically masked autoencoders, MAE, has been widely used for unsupervised learning in computer vision. However, the necessity of dense self-attention within mask tokens for effective representation learning is questioned. In response, CrossMAE is introduced, which uses cross-attention for decoding, allows partial reconstruction of masked tokens, and incorporates interblock attention. Surprisingly, CrossMAE achieves comparable downstream performance to MAE while being more efficient, demonstrating the potential of this approach. Section: Masked Modeling. The concept of masked modeling involves learning representations by reconstructing a part of the input that has been hidden or masked. This approach has been widely used in the field of natural language processing, NLP, with models like BERT and GPT leading the way. These models use a bidirectional transformer and autoregressive, causal masking, respectively, to demonstrate capabilities like few-shot learning and multitask learning. In the realm of computer vision, early works like stacked denoising autoencoders and context encoder used masked image modeling for denoising or representation learning. With the rise of transformers as a backbone vision architecture, researchers are now exploring how to apply the success of language sequence modeling to vision transformers. Models like BAIT, MAE, and SIM-MIM are some of the early works that have explored this approach. However, these models have found that a higher mask ratio is needed to learn good visual representation compared to NLP models. Recent works have extended masked pretraining to hierarchical architectures and have studied the role of data augmentation. There have also been successful applications of masked pretraining for video, language vision, and multimodal pretraining, as well as for learning good representations and reconstruction capabilities. However, BERT-style pretraining requires heavy use of self-attention, which increases computational complexity. Models like Pixel Transformer and DiffMAE use cross-attention for masked image generation and representation learning. In this work, we aim to investigate if high-quality reconstruction is necessary for learning good features and if the entire image needs to be reconstructed for representation learning. Cross-attention is another technique that has been widely used in computer vision. It is a cost-effective way to perform pooling from a large set of visible tokens. It can be seen as a form of pooling that weighs different features. It has been used to improve ImageNet classification performance and to efficiently process large volumes of multimodal data. It is also used for object detection. In this work, we introduce CrossMAE, a model that uses cross-attention instead of self-attention in the decoder for reconstruction. This allows us to achieve further efficiency gains by reconstructing only a subset of mask tokens for faster pre-training. We also propose interblock attention to allow different decoder blocks to focus on different encoder features, which enhances feature learning. Masked autoencoders, MAE, are used to pre-train vision transformers, VITs. Each image input is first divided into patches, and then a random subset of the patches is selected as the visible patches. These visible patches, along with a learnable class token, are fed into the VIT encoder, which outputs a set of feature latents. These latents, along with the sum of the positional embeddings of the masked patches and a learnable mask token, are passed into the MAE decoder. The decoder outputs are then passed through a fully connected layer per patch for image reconstruction. The loss is applied only to the masked positions, while the reconstructions for visible spatial locations are discarded. In this work, we aim to answer two questions. Can good representations be learned if masked tokens can attend only to visible tokens? And can we improve pre-training efficiency by reconstructing only part of an image? Section Summary. Masked modeling is a technique used in natural language processing, NLP, and computer vision to learn representations by reconstructing a masked portion of the input. While BERT-style pre-training requires heavy use of self-attention, recent works explore the use of cross-attention for more efficient representation learning. In this work, the authors propose CrossMAE, a method that uses cross-attention instead of self-attention in the decoder for faster pre-training by reconstructing only a subset of mask tokens. They also introduce interblock attention to allow different decoder blocks to focus on different encoder features, enhancing feature learning. Section: Reconstruction with cross-attention. We've developed a method to address the first question, which involves replacing the self-attention mechanism in the decoder blocks with cross-attention. In simpler terms, our decoder uses a type of cross-attention where the queries come from the output of previous decoder blocks. The keys and values are derived from the encoded features. In our basic model, The output from the final encoder block is used as the key and value tokens for all layers of the decoder. We found that using a weighted mean of selected encoder feature maps can be beneficial. The residual connections in each decoder block allow for iterative refinement of decoded tokens as they progress through decoder blocks. Our decoder differs from the original transformer architecture as it omits the precursory causal self-attention stage before the introduction of multi-head cross-attention. This, along with the fact that layer normalization and residual connections are only applied along the feature axis but not the token axis, allows for the independent decoding of tokens. We evaluate this design choice in the ablation study section to determine its impact on performance. Given the difference in the dimensions of the encoder and decoder, we adapt the visible features to the decoder's latent space using a multi-layer perceptron, MLP. However, in our model, as encoder features are integrated at various decoder blocks, we embed the projection within the multi-head cross-attention module. This approach also mirrors aspects of perceiver I/O, where cross-attention is used to amalgamate features relevant to the task at hand. Our method decodes the masked tokens in a way that is more similar to the traditional transformer paradigm. The fact that our model uses cross-attention rather than self-attention in the decoder blocks brings an additional benefit over the original architecture. Since masked tokens are decoded independently and there is no exchange of information between them, to obtain the reconstructions at a specific spatial location, our model only needs to pass the corresponding masked tokens to the cross-attention decoder. This allows for efficient partial reconstruction in contrast to the original architecture, which needs to pass all the masked tokens as the input of the decoder blocks due to the existence of self-attention in the decoder blocks. To address the second question, rather than decoding the reconstruction for all masked locations, we only compute the reconstruction on a random subset of the locations and apply the loss to the decoded locations. We name the ratio of predicted tokens to all image tokens as prediction ratio and the mask ratio. Then the prediction ratio is bounded between 0 and the mask ratio. Because we are sampling within the masked tokens uniformly at random and the reconstruction loss is a mean square error on the reconstructed patches, the expected loss is the same as in the original model, while the variance is the mask ratio divided by the prediction ratio times larger than the variance in the original model. We find that scaling the learning rate of the original model to match the variance, i.e., setting the learning rate as the prediction ratio times the original learning rate divided by the mask ratio, helps with model performance. Since cross-attention has linear complexity with respect to the number of masked tokens, this partial reconstruction paradigm leads to a decrease in computation complexity. We find that the quality of the learned representations is not compromised by this approach. Our model combines the feature of the last encoder block with the mask tokens as the input to the self-attention decoder. This design poses the latent feature as an information bottleneck. It leaves no room for any residual connection for the decoder to leverage early encoder features, since the decoder blocks sequentially update and improve on the decoded features. In contrast, the cross-attention decoder in our model decouples queries from keys and values. This adds flexibility as different cross-attention blocks can take different feature maps as keys and values and thus no longer need to only use features from the last encoder block. Instead of manually selecting the feature for each decoder block, we propose interblock attention for feature fusion for each decoder block. Similar to the inter-patch cross-attention that takes a weighted sum of the visible token embeddings across the patch dimensions to update the embeddings of masked tokens, interblock attention takes a weighted sum of the visible token embeddings across different input blocks at the same spatial location to fuse the input features from multiple blocks into one feature map for each decoder block. Each decoder block takes a weighted linear combination of encoder feature maps as keys and values. For each key, value token and decoder block in a model with encoder depth, we initialize a weight. Then the token is defined as the sum of the product of the weight and the feature map. In addition to feature maps from different encoder blocks, we also include the inputs to the first encoder block to allow the decoder to leverage more low-level information to reconstruct the original image. We can select a subset of the feature maps from the encoder layers instead of all feature maps. This reduces the computation complexity of the system. We show that using the weighted features rather than simply using the features from the last block greatly improves the performance of our model. Interestingly, as we will show, early decoder blocks focus on the information from the later encoder blocks, and later decoder blocks focus on the information from the early encoder blocks in the process of learning to achieve better reconstructions. Section Summary. The proposed method replaces the self-attention mechanism in the decoder blocks with cross-attention, allowing the decoder to utilize encoded features as keys and values. This enables independent decoding of tokens and efficient partial reconstruction. Additionally, interblock attention is introduced to fuse input features from multiple blocks into one feature map for each decoder block, improving the performance of the model. Section Experiments. In our experiments, we used a self-supervised pretraining method on ImageNet -1K, following the COMO model. We kept most of the hyperparameters the same as COMO, except for the learning rate and decoder depth. These parameters were first set using the VIT base model and then applied to both VIT small and VIT large. Both our model, CrossMAE, and COMO were trained for 800 epochs. More details about the implementation can be found in the supplementary material. We evaluated the performance of our model using ImageNet classification. We used end-to-end fine-tuning and compared the top 1 accuracy. We tested 2 versions of CrossMAE, one with a prediction ratio of 25%, meaning it predicts 1/3 of the masked tokens, and another with 75%, predicting all masked tokens. Both models were trained with a mask ratio of 75% and a decoder depth of 12. The results showed that CrossMAE performed better than the original COMO model when trained on the same VIT-B encoder in terms of fine-tuning accuracy. This suggests that replacing self-attention with cross-attention doesn't reduce the quality of the pre-trained model for downstream classification. CrossMAE also outperformed other strong models like Dino, COCO v3, BAIT, and MultiMAE. We also evaluated our models using object detection and instance segmentation, which require a deeper understanding of spatial relationships than ImageNet classification. We followed the VT-DET method, which uses a vision transformer backbone for object detection and instance segmentation. We compared our results with 4 other models: supervised pre-training, COCO v3, BAIT, and COMO. CrossMAE performed better than these models, suggesting that its performance on ImageNet correlates positively with instance segmentation. As the model capacity increased from VIT-B to VIT-L, CrossMAE's performance scaled similarly to COMO. We also compared cross-attention and self-attention. CrossMAE, which uses a cross-attention only decoder, performed better than the original COMO. We found that using both cross-attention and self-attention together didn't lead to additional benefits in terms of fine-tuning performance. This suggests that using only cross-attention is enough for learning good representations. We tested different mask ratios, the ratio of mask tokens to all tokens, and prediction ratios, the ratio of reconstructed tokens to all tokens. Our method wasn't sensitive to changes in the number of masked tokens. Although predicting the reconstructions from all the mask tokens led to the best pre-trained model, the difference between full prediction and partial reconstruction was small. Specifically, CrossMAE could be trained to reconstruct as few as 15% of the tokens in the decoder, achieving similar downstream fine-tuning performance as the original COMO model, which required 100% of the tokens. This suggests that a good representation can be learned by reconstructing only part of an image. We also varied the number of encoder feature maps that were fused with our interblock attention. Using only the last feature map led to a minor degradation of performance compared to using all feature maps. However, adding even a subset of feature maps improved the performance of CrossMAE, with the best performance reached when 6 feature maps were fused. This suggests that CrossMAE doesn't need all feature maps to achieve its best performance. We found that using a decoder of 12 blocks slightly improved downstream performance compared to shallower decoders. CrossMAE performed as well as the original COMO even with as few as 1 decoder block, showing its efficiency in pre-training vision transformers. We also tested CrossMAE on longer token lengths by increasing the image resolution without changing the patch size. As the resolution increased from 224 to 448, the image token length increased from 197 to 785, which is a significant challenge for existing methods. We chose the CrossMAE variant with a 25% prediction ratio for higher efficiency. We found that the classification accuracy positively correlated with the input resolution, suggesting that CrossMAE can scale to long input sequences. Section summary. The authors conducted experiments to evaluate the performance of CrossMAE, a self-supervised pre-training method, on various tasks such as ImageNet classification, object detection, and instance segmentation. They found that CrossMAE outperformed vanilla MAE and other strong baselines in terms of fine-tuning accuracy. The authors also explored different ablations, such as the impact of cross-attention versus self-attention, mask ratio, prediction ratio, interblock attention, decoder depth, and input resolution, and provided insights into the efficiency and scalability of CrossMAE. Section: Visualizations. To delve deeper into the characteristics of the updated reconstruction objective, we've developed a method to illustrate the reconstruction process of CrossMAE's decoder blocks. We also display the weights assigned to each encoder feature map to give a sense of how interblock attention works. Instead of just showing the final reconstruction, we suggest a more detailed visualization method that lets us accurately comprehend the impact and contribution of each decoder block. This is made possible by two key observations. Firstly, transformer blocks have residual connections that link their inputs to their outputs. We label the output of decoder I as F_I and its residual path as G_I, F_I1, with F_I being the sum of F_I1 and G_I, F_I1. Secondly, the output of the last decoder block is processed by the reconstruction head H to create the reconstruction. It's important to note that H is linear because it consists of two linear functions, a layer norm and a linear layer. Let's denote the decoder depth as D, the input to the first decoder block as F_0 feet, and the final reconstruction as Y. We can define Y recursively as H, F_D1, plus G_D, F_D1. If we expand this and consider the linearity of H, we can express Y as the sum of F_0 feet and the outputs of all the residual paths, G_I, from I equals 1 foot to D. This breakdown allows us to represent the reconstruction as a stack of images, where the sum of all the layers gives us the final reconstruction. We display this visualization and analyze the contribution of each layer to the final reconstruction. We adjust the output by patch mean and standard deviation for visualization purposes. From our visualization, we notice that different decoder blocks have different roles in reconstruction, with most details appearing at later decoder blocks. This supports the theory that early encoder blocks need to provide low-level information, which justifies the use of interblock attention. We also illustrate the attention maps of interblock attention. This reveals that the CrossMAE model naturally uses interblock attention to allow the later decoder blocks to concentrate on earlier encoder features for reconstruction, and vice versa. This further supports the need for different decoder blocks to pay attention to different encoder features, which aligns with the performance improvements achieved with interblock attention.